keep everything elementary. So I hope he's sticking to it.
Thank you very much for your words, and again to the Fernald's Foundation for offering this opportunity and these outstanding lectures. So I will start just by recalling the context that I was around the end of my lecture yesterday. So we have a family A of abelian varieties, and the family is parametrized by an algebraic variety S. So we have a map from A to S, and our abelian varieties are just the fibers of this map. And as a matter of notation, we call G the common dimension of these abelian varieties. So we saw examples coming from the Poncelet game, for instance, where the abelian varieties are elliptic curves. That was, and also another example was the one of the Legendre family that we shall meet again in the lectures. And then we have a section, a family of points. So a family of points parametrized by the same algebraic variety S, P of S, which belong to A of S, AS. So this is called also in technical terminology a section, because it goes from here to there, and composing with the map pi, we get the identity. And our task is to investigate the values of S, of the small s, where this point becomes torsion in AS, and we shall assume that it is not identically torsion. So, as a matter of notation, again, we call Tn the set of small s and capital S. Here we work over the complex numbers, such that n times P of S is the origin of AS. And we do this for all positive integers. So we assume to say that P of S is not identically, that P is not identically torsion means that Tn is not the whole space for each positive integer n. So this is a basic assumption. If this were not the case, there is little to study. So the task is to understand the distribution of the points, the so-called torsion values. What I call torsion values, namely the set, the union over all positive integers of the sets Tn. And I have illustrated yesterday with some examples how this appears in a number of contexts, and we shall see some further examples as the lecture goes ahead. So the aims, the main tasks. So let us observe that this remark will be clear later, but it turns out that these sets have codimension generally, which is generally equal to G, so of the same dimension of the fibers. But this generally has to be interpreted. In fact, the codimension may be smaller. And sometimes also it happens, it may happen.
That's right, but we can.
Yes. happen that the Tn are empty. So this is a general remark. So the aims. The first point is to prove density. Prove density of the torsion values in the complex topology. And for this to be true, one at least must assume, so under the condition that the dimension of the space of parameters is at least the dimension of the fibers. Otherwise, we have no hope. But other conditions will have to be assumed to obtain this. And I state two conditions, which are natural and necessary. The first condition is that the set of multiples of the section is Zariski dense in the whole space. If this is not fulfilled, then it is not a big restriction, because we may in any case, go to the Zariski closure, which will be, again, an abelian family. And so by restricting the family to the Zariski closure, this may be achieved. So this is a first technical condition, but natural in a way. And the second condition that we shall assume is that the family A has no constant part. This I don't define formally now, but I will give examples later. Let me just, roughly speaking, what I mean by this. I mean that, for instance, a case when the constant part is everything is when occurs when all the abelian varieties AES are isomorphic. Perhaps they may be defined by different equations, but if they become isomorphic, all of them, then we say that A is a constant family. And we want to exclude this case for reasons that I don't pose on now. But we want to exclude not only this, but that there are not, that the space of parameters can't be fibered with curves where the abelian variety is constant. So in a way, we are taking the minimal space of parameters, just to parameterize those AES which are different. So this will be an assumption that I will make. So results, here I will state later, today and on Thursday. The results here are somewhat scattered. A result not proving density, but proving less than this, that I will soon state, is due to Manin and goes back to 1961. And then other results, for instance, are due to Krichever in the case of hyperelliptic families. And more recently to Voisin. And in the last lecture, I will state a recent result obtained jointly, more recently, a result obtained joint with Yves André and Kodaira. I will state later. So a second task occurs when when this condition is not satisfied, when the dimension of the parameter space is small, smaller than the dimension of the fibers, and then we expect that the torsion condition will be very seldom satisfied, and we may expect even finiteness. So in this case, the task would be to prove finiteness. Here, this finiteness has been actually conjectured explicitly by Richard Pink, and in some cases by Boris Zilber. Pink has much more general conjectures, but they include, as a special case, the finiteness. As to proofs of this, also they are known only in quite special cases. In joint work with Masser, we proved this under the assumptions that I said for dimension of S equal 1, so the case of curves. This is quite special, but at least it may be done. For dimension of S greater than 1, very little is known. And there are only scattered examples proved by Habegger. So, okay, so this is the, so I will concentrate in these lectures more on the, to prove the density, on the existence side. So let me also, so speaking of density, also a remark that I would like to do is that one might look for density also in the p-adic case, and for instance there it is never true. So let us stick to the complex case. So now I want to introduce an useful object to deal with such a problem, which is the so-called Betti map. The terminology is uncertain who introduced it, but as far as I remember, I heard this word from Daniel Bertrand. Anyway, the Betti map, as you will soon notice, Betti had nothing to do with this map, but the map regards the homology groups, and so the Betti enters into the picture in this way. So let me describe first, recall the case of elliptic curves, and actually of a single elliptic curve, so not even a family. So the elliptic curve, complex elliptic curve, is in particular a complex Lie group. So there is a tangent space at the origin, which is maybe identified with C, and there is an exponential map, elliptic exponential, and this map has actually is a homomorphism for the additive group of C turns out to be a homomorphism to the complex points of E, and the kernel of this map is a lattice. Let me denote it by lambda. So it will be a lattice of maximal rank in C. It will be generated over Z by 2 complex numbers that I denote presently with rho 1, rho 2. They are linearly independent over R. So we obtain an analytic isomorphism of the quotient of C mod lambda with E. So the quotient is a torus. And this picture is, of course, this isomorphism occurs only analytically. So in a way, it simplifies the group law on E because now the group law here becomes additive. On the other hand, we are in a transcendental context. So here the curve is algebraic, and when we take the points inside this space, they lose their arithmetic properties, and so we lose something and we gain something. Anyway, the group law becomes much more simple analyzed inside here. So indeed, if we have a point psi in E, we may take, this is surjective, we may take a point psi tilde called an abelian logarithm, which is sent to psi by the exponential. And now this point psi tilde will lie in C. There are many representatives that we may take because we may add points of lambda. But let us take one representative, and we may express it in the form x rho 1 plus y rho 2, where now x and y are reals. They are real numbers. They are not uniquely determined, but they are uniquely determined up to integers. So this is called an abelian logarithm, and these coordinates are important in the definition of the Betti map. So when we have a family, we may do the same for all values of the parameter. Let me, for the sake of example, take the Legendre family. So it is given by an affine equation. So S here is the parameter. It has to be different from 0 and 1. And then we have the point at infinity. So this curve, we denote it by LS. So it is defined by that equation. So each of these curves for each complex value of S will be represented as a complex torus. And in this case, there are nice explicit formulas for these generators, which are called periods. Let me write them down. For instance, in the region defined by when S and 1 minus S are simultaneously less than 1, this is this region here. In this region, we may represent the periods by hypergeometric series. Here we have binomial coefficients, and rho 2 may be taken very similar expression, but now so these are hypergeometric series already studied by Euler and Gauss. They satisfy the Gauss equation, differential equation, which is the following one. Here by dash I mean derivative. So both rho 1 and rho 2 are solutions of these Gauss differential equations, and actually they form an independent set of solutions at every point. So these functions are defined by this series only in this region. So this is a local fact. We can't have a global expression like that, and which is in a way annoying, but in fact is a source of information. Because we have monodromy maps when we travel going around one of the singular points of the equations, which are 0 and 1, these functions do not remain what they were, but when we end the circle, they will change according to a certain monodromy action, which I will recall. Anyway, so this is the situation for a family. And now, let us take our section, our point. Yesterday, I chose the point, for instance, P of S, defined by S plus 1. So in coordinates x, y, where S plus 1, and then here the square root. Of course, this is not well defined, but it is well defined up to sign, and I will forget about this small technical point now. So for each complex value of S, we may do this process, and we shall have a family of exponential maps and a family of abelian logarithms like this. So let us do this. We shall express the abelian logarithm of the point at S like x of S, rho 1 of S, plus y of S, rho 2 of S. And now x of S, y of S will be real. We can't do this globally. But for instance, we can do this in this open set, and actually, for each point which is not singular, we may find an open neighborhood in which this representation holds. So we obtain locally this map. It associates to S the pair of coordinates, and this is the Betti map. It depends on the section, of course, but I omit, not to complicate the notation, I omit reference to the section. So when the section is given, when the family of points is given, then the Betti map will be this. It is not uniquely determined, but locally it is uniquely determined up to integers. So we have this map. And now what is the usefulness? The usefulness comes from the following remark. The point S naught is a torsion value. If and only if the Betti map calculated in that point has rational entries. So this gives a condition of rationality which is much simpler than looking at the torsion equations that we would obtain in the algebraic model. When we operate in the algebraic model, the group law that I alluded to yesterday gives rise to very complicated equations of growing degrees. And these equations may be useful for some purposes, but they also become complicated and useless for other purposes. Here we gain an interpretation, simple interpretation in terms of rational numbers. So this in a way transforms the problem into a problem of looking at rational points, which is a familiar problem studied in number theory. However, the context now is transcendental, because the coordinates of the point here you see are algebraic, but these coordinates here will become highly transcendental. So we have a number theoretical Diophantine problem on a transcendental context. And however, these problems have been studied. For instance, Bombieri and Pila studied, it is now many years, they studied, for instance, the distribution of rational points on transcendental curves. So not only on algebraic, which was the most common topic for the number theory, but on transcendental arcs, and found that these points could be well estimated. And then this also went ahead with other works of Pila and Wilkie in higher dimensions. So we have now results on the distribution of rational points on transcendental varieties which are very strong and may be applied to some of the issues I have described, but mainly to finiteness. They prove that the rational points are few. So these results help improving in going in the second task, the task of finiteness, rather than proving the density. That is the main thing that we have in mind in these lectures. So there is a Betti map also for other abelian families of higher dimension, but I skipped the formal definition that you can easily imagine. There will be 2G periods now, and for the rest, the definition is entirely similar. So I skip it. As I told, the Betti map has monodromy transformations that I shall use in proving a special case of a theorem of Manin. So the theorem of Manin is the most important theorem regarding the Betti map. So Manin, in a more general context of abelian varieties, the first thing he asked is, when can it happen that both these coordinates are constant? When can it happen? Notice that if they are constant, for instance, we see that also the abelian logarithm of the point continues to verify the Gauss differential equation. So Manin was interested in the constancy just for this reason, because he sought in the paper of 1961 that I mentioned, he sought the kernels of differential operators, and he was faced with this problem when the Betti map is constant. A comment about the Betti map is that it is a real map. So it is not anymore an analytic map. This is a locally analytic map. The periods are locally analytic, but the Betti map is not a complex analytic. It is a real analytic. This is something, but not as strong. However, another important property is that its fibers are complex analytic. If we fix the Betti map, we obtain complex analytic equations. So it has a double behavior, so to say. So Manin theorem. This is only one of the results that he had in this paper, but was a crucial one to prove the rest. So suppose that the family A has no constant part. Then the Betti map is constant. He didn't call the map the Betti map, but if and only if the section P is identically torsion. So in other words, the Betti map may be constant only if these constants are rational. So in one direction, the theorem is easier. If P of S is identically torsion, then these functions assume rational values, and being continuous, real analytic, so continuous, they must be locally constant. So, but the converse is more subtle. Excuse me? Betti map constant, I mean that these functions are constant in S. Well, the Betti map is associated to the section. The Betti map depends on P. I omitted the notation for, but it depends on the section. Each section has a Betti map of its own. So it tells if the section is identically torsion just by looking at the. So constant part. Let me give just an example to show what happens when the constant part is big. Constant part. I give an example. Take this family of elliptic curves. So the equations are not constant because this S is varying, but if we perform a substitution, we send X into S to the 1/3 times X, and an analogous substitution on Y, then we have an isomorphic curve when everything, the S cancels, and this becomes isomorphic to this curve here. So in this case, the equation is not constant, but the curve, all the curves are isomorphic. And we don't want this because otherwise the theorem of Manin would become false without this assumption, because we would go to a constant point, and the constant points may have constant Betti maps without being torsion. So this is just a remark on the meaning of this condition. And so this is a necessary condition. And it is, so what is relevant for us is another remark that I want to do. If we take a section with constant Betti map, so these sections exist locally, because I may just define P tilde by putting here two constants that I may choose and take the exponential of these points. So I will obtain locally a section with constant Betti map. The issue is that this section will not be algebraic. So here, the exponential of this P tilde has algebraic coordinates. It is here that we have the information. So, but if we start, nevertheless, we can start with, if we define certain q tilde of S, for instance, just by putting two complex numbers, and we take q by definition the elliptic, the Legendre exponential of q tilde, then we get a locally analytic section. And this is interesting. This section will never assume torsion values unless these two numbers are both rational, will never assume torsion values. So here we see the relevance toward our issue. If we have a section with constant Betti map, then torsion values do not even exist. Not only they are not dense, they won't exist. But this section, by Manin theorem, cannot come from an algebraic family. By the way, these abelian logarithms with constant Betti map are relevant. They satisfy the Pell equation of type 6, which appeared also in the, surprisingly to me, in the work by Bourgain, Gambert, and Sarnak that I quoted yesterday. So for reasons that are apparently different, but maybe not. So this Pell-Levé is Pell-Levé equations of type 6 are equations of the second order, differential equations of the second order, where the second derivative is a polynomial of degree 2 in the first derivative with coefficients which are rational functions in the variable and the function. So, but they appear in a number of contexts. So, I would like to also to state corollary of Manin's theorem before sketching a proof for the case of Legendre. Corollary of Manin's theorem is that if we are in the case of genus 1, so if the fibers are elliptic curves, then if P is not identically torsion, the torsion values are dense. So this corollary shows the relevance of the Manin theorem for our aim. This is not difficult to prove. Let me sketch an argument. First of all, let us assume for simplicity that S is a curve. This is not restrictive because we can take a general curve inside S if it has dimension greater than 1. So we have this. Now locally we have the Betti map of the section. And this is real analytic. It goes from an open neighborhood in an open disk in the complex plane, like this, or even smaller. So it sends an open disk to the real plane. And it is an real analytic map, so it may be regarded as a real analytic map of a disk in the real plane to the real plane. And now we may apply the implicit function theorem. if the image, what can it be? The Betti map could be constant, but then we have the Manin theorem and we deduce that the section is torsion. Otherwise, the image can be of dimension 1, so contain arcs of real curves. If this would be the case, then the general fiber, by the implicit function theorem, the general fiber of a point in this curve would be also an arc of a curve. Because the implicit function theorem says that locally, when the differential is not 0, we can view the map as essentially as a linear map. But the fibers of the Betti map are complex varieties. So if they contain, if there is an arc of a real curve in the fiber, then since we are inside the complex numbers, then it must be everything. So this intermediate case is not possible. The map is either constant or surjective, locally surjective, and then if it is locally surjective, this is the third alternative, then it obtains all the values in a disk, and in particular it obtains rational values which are dense, and this gives the torsion values. So this, I hope, shows the relevance of the Manin's theorem in the context. Actually, in the work with Andrea and Kodaira that I mentioned, we have tried to go more inside. So the constant case means that the differential of the map is 0. We have tried to study the rank of the differential. So to study the cases when the rank is maximal. And we have some results in this direction, and also improved recently with collaboration with Gao. But this I postpone to the third lecture. Now what I would like to do is to sketch a simple proof of the theorem of Manin. That actually appears in his paper. He also starts from the elliptic case. So, sketch of proof of Manin's theorem for the Legendre case. So let us assume that that this elliptic logarithm of our section has constant Betti map. Now the proof works by performing an analytic continuation. So I draw again these two circles of radius 1, centered and at 0 and 1 respectively. These 2 points are just the singular points of the differential operator, which, so they are crucial points. So we can pick now a point, for instance 1/2, and analytically continue all of these functions going counterclockwise around 0, for instance, in the shape, in the pattern that I have drawn. So what happens? This P tilde of S will possibly become something different after one circle. But since P tilde comes from an algebraic function. The algebraic function has finite monodromy. So after performing k times the circle, after going k times around 0, where k depends only on the section, is a positive integer, this P tilde of S will be another determination of the same function. For instance, here you see we have a square root. The square root has, the sign is not fixed, but if we go twice around, we find the same value of P of S. And so the abelian logarithm will be the abelian logarithm of the same point, which means that it will be the former one plus integer multiples of the periods. So after going k times around 0, P tilde of S changes by something of the form m times rho 1 of S plus n times rho 2 of S, where m, n are integers. Now let us see what happens if we look at the right side of the equation. Rho 1, I have written it explicitly, rho 1 is given by this hypergeometric series, which is convergent. So rho 1 has no problem in going around 0. So rho 1 will remain unchanged. Rho 2 will not remain unchanged. There are the monodromy transformation of the hypergeometric functions. And these are not completely trivial to obtain, but they are part of classical mathematics of the 19th century. And the rho 2 will be changed to rho 2 itself plus 2k times rho 1. So the matrix, the monodromy matrix is this one. This is the monodromy matrix for rho 1, circling, no, yes, for rho 2. And if we apply this k times, we obtain 2k here. So now we compare the things. So we compare the things. We have then that this expression here will go into x naught rho 1 plus y naught times rho 2 plus 2k rho 1. So this is the previous expression plus 2k y naught rho 1. But now we know from the first observation that this changes by integer multiples, linear combination with integer coefficients. So 2k y naught has to be an integer. And this proves that y naught is rational. And a similar argument with the other singular point proves that also x naught is rational. So this is the simple proof of Manin's theorem for the Legendre case. In general, I want to try to reproduce. Things are more complicated, of course. He argued, however, in the same pattern, same way. what he needed, what he lacked in general, one does not know the monodromy transformation of the abelian logarithms. These are known and explicit in the Legendre case, but there is little hope to obtain such explicit things in general. So he had to prove somewhat that the monodromy was large enough so to be able to reproduce the argument with any number of periods. And for this, he didn't use directly the monodromy, but following, as he says in the paper, a suggestion of Shafarevich, he used the Mordell-Weil group that it is finitely generated. And this, by using division in the Mordell-Weil group, he was able to introduce this information is in fact a monodromy information. The finite generation allows to understand something about the monodromy. And this was enough for concluding the proof. So, in our, let me anticipate that in our work with André and Corbaia, so monodromy is used implicitly. So Voisin, for instance, in her work, uses monodromy in a certain way. We don't use monodromy explicitly, but we use it implicitly through a theorem of André, which proves the algebraic independence of the abelian logarithms over the field generated by the periods. So this is somewhat a functional transcendence. André and Daniel Bertrand, there is also work by Deligne in this sense. They proved algebraic independence theorems which contained a monodromy information because in fact the algebraic independence is related to the differential Galois group, and the differential Galois group is the Zariski closure of the monodromy for Picard-Fuchs equations that were studied deeply by Katz, for instance. And this is the ingredient. So monodromy plays a role, an important role, whatever proof one wants to follow in this context, apparently. At least the known proofs work like that. So she exploits monodromy, but in apparently different way. In fact, she can deal only with G equal 2, because to understand the monodromy action in general is more complicated. But, so for this context of the torsion, the differential equations that she does not use give the further information through the theorems of André and Bertrand. So the differential equations, are implicitly unavoidable, or at least greatly simplify things. So, in the few minutes that are left, I would remark that another proof of the infinity of torsion values for the Legendre case, for instance, a different approach, but this works really only for the Legendre case. It comes from Diophantine equations over function fields. So, to show how this happens, let us write n times our point P of S. Let us go back to the algebraic context. Now the Betti map disappears for a moment. We go back to the algebraic context, and this n times P of S where the operation is, of course, the operation on the curve, we may write it as with coordinates xn of s, yn of s, and these coordinates satisfy the equation of the Legendre curve. So the torsion, when do we obtain a torsion value? If S naught is a torsion value corresponding to torsion, to torsion n, then this means that x naught is a pole of this rational function, because the point at infinity is our origin. So to have only finitely many torsion values would mean that all of these functions would have poles restricted to the same finite set. And so they would be integral points over a function field, and this violates, for instance, the Ziegel's theorem over function fields, which is a purely Diophantine statement. So this approach shows the infinity of torsion values, and by the analytic argument, where the Betti map enters again into the picture, to have infinitely many of them means that the Betti map is non-constant, and then we have the same deductions as before. Unfortunately, this approach does not work, at least I cannot make it work. There is not even an analogy for higher genus. So this is alternative, but only for elliptic case. So for today, I will stop here. Thank you very much. Thank you.
Can you say a word why the Betti case never works?
We haven't, this is a work in progress with a young student, Brian Lawrence. But the idea is like the fact that torsion points on a given abelian variety are discrete in the p-adic case. And so even when we move by little, there remains a discrete structure. So there can be, however, accumulation points, but which tend to the boundary of the base. So if we take a closed set which is of good reduction, so when everything works fine, then the set should be discrete, even. So not only not dense, but even discrete.
Is that a paper of Manin, the one we need? The Manin-Manfred conjecture, does it come from that paper?
This may be, but in this case, he proves the Mordell conjecture over function fields. By the way, there were errors, but not in the part. There were errors corrected, and then everything works fine. But
I'm asking about the history of the Manin-Manfred conjecture for abelian varieties and special subvarieties, which is closely connected, of course.
yes.
Well, what's the history of that?
So this apparently does not come out from that paper. And as far as I remember, the Manin-Manfred was formulated independently by the two. And surprisingly, it seemed to appear even before the toric case, which was formulated by Lang. But most probably he was led to that by this that you're saying. Yeah.
More questions? Yes.
So what gives the results is on the dimension of S. And actually, every result should be on the decentral dimension of
Yes, one can weaken the hypothesis of no constant part, if I understand correctly your question.
My question is, if we assume these two, do we already have the essential dimension? The essential dimension of S is already the dimension of S or not? What is essential dimension?
The dimension in the moduli space. Oh. So in this work, we assume simply that the essential dimension of S is equal to the dimension of S. But surely something can be done also when the dimension goes down, but supplementary assumptions have to be made.
Okay, so these two assumptions doesn't imply.
Yes.
I'm glad to see that you got Yves Andre back into transcendence.
Oh, yeah.
Yeah. Well, it seems that I think we're ready to end this session, and we will continue on Thursday at 5 o'clock. Is that right? 5. Anyway, it's announced.
Thank you very much. Thank you very much.